the last presentation of today, and it's for myself. Now we've been talking about OPC UA, what can you do with it, a lot of products being presented, and every now and then someone asks how fast is it, and so far I haven't even been able to say anything really about that, but now we made some measurements and I can show you something about that. But first, a little bit about Prosys OPC, already been mentioned here today by Matthias, for example. So we are providing Java-based applications, and our main expertise is on the Java side. For IoT, Java is a workable platform, and Oracle, for example, is making big efforts to make it available. We have demonstrations here with Raspberry Pi running natively Java platform, standard Java platform on Linux. We have Android clients. Android is running Java natively, and so on. So Java is kind of the only really cross-platform solution nowadays. You can just write once and use the same application as is in all these platforms. Our flagship product is the Java SDK, which we have put a lot of effort. The first release was already 2010, and since then we've just been improving it, and also we've been making some applications with the SDK to prove for ourselves that it works, and also to provide some really useful applications for you. These three applications are usable for testing connections, learning OPC UA basics, the simulation server and the clients, and we're also working on these off-the-shelf applications, file transfer and history and application. I already presented those last year and promised that they will be available by the end of the year, and I can do it again. They will be available by the end of the year. Yeah, it turned out there's a lot of details, and I wanted to make sure that once we really ship those products, they are in good level, and we won't need to go and rework on them and just make it too fast release kind of. Java SDK, so you develop once, deploy anywhere. It takes care of all the communication details. The same goes with all these toolkits that have been mentioned today. The idea is that you don't need to know all the details that are going there in the communication. You just need to use the SDK, and it will provide you the full OPC UA functionality. Client and server available, of course, and we support all the standard and custom information models that we've been talking about today through code generation, and you can use UA modeler to build your own models. Java SDK is also certified for compliance, which means that it's guaranteed by OPC Foundation that it's interoperable with the other OPC UA applications, and that's very important. I think in general with the OPC UA we are in a very high level already with other products, because all the SDKs have been available for a long time and they've been interoperable and tested with each other. So it really doesn't matter which applications you are using. In practice, when Stefan was going through all these different cases that have been happening in Europe and all over the world, there were several cases where the actual platform is made with C++ or .NET, for example, but I know that there are Java clients that are also connecting to those systems. So a lot of people are working with different platforms at the same time, and there are no real issues with those. The code generation with the Java SDK, it works like this. We have the UA modeler where you can generate or create your own information model, and with the UA modeler you can generate C++, C# for the Unified Automation SDKs. And for Java, you export the XML, which is the standard UA node set XML format that OPC Foundation has specified. You can export the models with the UA modeler. On the other hand, you can get these models from the standard organizations or from OPC Foundation. The standard models are available with these node sets. And then you can just use the Java code generator as a separate application, and it will just generate you Java classes respective to the OPC UA object models. And then you can work on real Java classes, Java objects, instead of going through some kind of OPC UA specific definitions. That's the idea. OPC UA client is like UA Expert, but it's based on Java, so you can use it in any platform, and it has a little bit different user interface. But in general, it's kind of a browser-like interface. You can have several connections at the same time. You have the address-based browser here, and then you can have different views. You can see the attributes, the data view, history view, event view. Also, the history events view is available. And for Android, we're also providing this free client application, which you can get from Google Play to your own phone, and you can connect to any OPC UA server and browse through the data and monitor data with it. This also used to prove that you can work on these environments with the SDK. If you need to kind of develop a custom Android user interface, you can use the SDK for that. The simulation server is providing you a simple server with a user interface, which you can also use to configure your own environment and simulate that one. In future, I hope we can also kind of integrate information models in the simulation server so that you can get even more out of that. At the moment, you can just create your own signals and use those from it. And finally, the historian application. The idea is that it's also an aggregating server, like the one that Fraunhofer is developing. You can bring in data from all different OPC UA servers and manufacturers and integrate everything in one OPC UA server, but also it will store selected information in a database and create history for the signals. Typically, a PLC, for example, doesn't keep at least not very long time history, so you can create a long time history database with this product. And the idea is that you can also use SQL or SQL queries to the database and get data out of it like that. But of course, OPC UA would be much more usable in general, but that depends on your higher level application, what's the capabilities. Okay, that was the quick show of the products, and then to the performance measurements. I have a few different setups that we have been going through, and work is still also going on. But at least we have something to present now. We are comparing different hardware. What's the effect of hardware here? We are comparing security with or without security. We are comparing Java against C++. That's an interesting comparison. And we are comparing different read types or kind of different service call types in general. In OPC UA, you have different service calls. I think the basic ones are read and write, of course. Then you can call methods. And of course, you can subscribe to changes and these kind of things. In general, you can read one item at a time, or you can make a big read and read thousands of items in one single call. And we are comparing what's the difference if you do it the wrong way, kind of. Okay, so the first measurements, we were comparing different hardware. The first one is a normal Dell laptop with 8 cores, and the other one is the Raspberry Pi, the old model with single core, 500 megabytes of RAM, running a Linux operating system. And the first comparison is the absolute time used by one encrypt method call. So at first we were just trying to figure out what's the impact of encryption. And we find out that on the laptop it's a fraction of a millisecond that one call takes, whereas on Raspberry Pi it takes around 4 milliseconds to do one encryption. But that's kind of the basic blocks. But then if we compare complete read calls made between applications running on the same hardware, we were testing with a byte array of 10 elements at first, and we find out that it's around 1,000 to 2,000 read calls per second on a PC that you can make, but only 30 to 50 read calls per second on Raspberry Pi. On the other hand, one call takes around half a millisecond without security in a normal PC, and if we use in OPC UA we can use just a signed security model where the data is not encrypted but it's signed that it cannot change during the communication. And then there's the sign and encrypt model where you also encrypt the whole message so that no one can read what's inside. If we apply the full security, the time on the normal PC doubles from half a millisecond to 1 millisecond per call. And surprisingly on Raspberry Pi it seems that, well, initially it takes 20 milliseconds for a call anyways, but the encryption doesn't seem to make it that much bigger. But then if we use bigger values, bigger elements, an array of 10,000 elements, the effect of encryption increases. Without security we don't see much difference at all, but with encryption, because the message size is increased, the time is increased. But it's not very remarkable on the normal PC, but on Raspberry Pi it doubles the time required for the encryption. Okay, then second setup. Now we are making remote calls, and we devised this kind of a setup procedure where we have a client running on this same Dell laptop, and then we have a server machine which is a little bit older model, only 4 cores, and not an i7 processor. And that was done in our office network, which is nowadays a 1 gigahertz network internally. And we are making asynchronous read calls so that the waiting delays don't matter. And we are instantiating 50 clients on the client application. That means client connections simultaneously. But they all running in the same application. So we start up all the client applications, they connect to the same server, and then we'll work on that. Then we compare if we're doing single reads, so that we read one value at a time, which means that we are actually making hundreds or thousands of read calls, or then we are just doing batch reads, reading all the values in one call. And we are comparing the Java against C++, namely Prosys OPC Java SDK, which has a sample console server application just out of the box, kind of, and also the Unified Automation UA demo server, which is available part of the SDK, but it's actually available as is also. Okay, so first the effect of programming language. We are doing single reads now, so one value per read call. And here we have a chart. We are showing that we are reading 100 values per client, 500, 1,000, and 5,000 values. And the blue line here is for the Java server, and the red line is for the C++ server. And this scale is here values per second. And it seems that the Java is actually faster. But we start both start on a kind of same level here. And for both, it seems that it tops here at 1,000 values. And after that, the performance degrades for some reason. But in general, we get around 10 to 30,000 values per second, which means actually 10 to 30,000 read calls per second. Okay, then we compare that with a batch reads, meaning that, okay, now we are just making one read call, but we ask for all these 100 to 5,000 values at the same time. So we have, of course, just one call going through the network, and then the time is taken just by processing the request on the server side. And in both of these cases, the servers have the values in the memory already, so there shouldn't be any extra processing in general. It's just for the kind of the performance of the SDK and the stacks in the communication. And in general, we get 10 times faster communication, 100 to 300,000 values per second. And now it seems that the Java server is faster up to around 1,000 values, but then it seems that the C++ server is starting to perform better after that. In general, I would say that they are performing in equal level, and this can be, the differences can be just somewhere we haven't been able to analyze where are the differences that explain these values. Also for the Java server, it seems that it tops here. It doesn't get faster even if we increase the number of values per read call. We don't get kind of any more data even if we use bigger calls. But with the C++, it seems that it looks linear in this scheme. So if we compare these batch reads to single reads, we can see it's around 10 times faster with the batch reads. So that's the measurements that we've done so far. As a conclusion, we can say that OPC UA is fast, up to 300,000 values per second. I think earlier today we heard that there would be some installations with 10 millions of tags that are updated once a second. But I think that's really not the case, that they are not read every second. Because in a normal automation system or anything that you're monitoring, the values are not changing all the time. And you are not, this is not kind of the way to do it, that you don't read all the values every second. Instead, we use, in OPC UA, we use the subscription model. And the subscriptions are made for just sending the changes, change notifications. And then you can really monitor millions of nodes, because only some of them are changing, and you can still get kind of, I would say, around 300,000 values per second through OPC UA. But that's the question we started figuring out how to test the performance through subscriptions, but that's not so simple after all to get a kind of good setup. So that's still a work in progress, but I'm estimating that we should be able to get some kind of similar amount of data through the subscriptions. But that in practical case, the subscriptions are always preferable, of course, because then you can limit the traffic just to what is changing, and that's a fraction of all the values that you're trying to monitor. Also, Java and C++ offer quite equal performance. And then the next step would be to compare to .NET. We started that comparison as well, but there were some issues that were uncertain about the .NET so far, so I didn't present those results yet. And also in general, we can say that embedded devices are, well, in this case, around 40 times slower. In general, 50 times something. But you need to be aware that, okay, you can use Raspberry Pi, it's still fast, but not as fast as a normal PC, of course. And, yeah.
But the scaling, I mean, you don't want to send 300,000 values with your Raspberry.
Yeah, that's true.
A few sensors maybe.
Yeah, exactly. Exactly. So you are not using the Raspberry for the same applications that you would use a high-level PC, of course. So in practice, it's not a bottleneck, I would say, also. And yeah, the batch reads are 10 times faster than single reads in fast networks. We had a 1 gigahertz network, so it doesn't have that big effect. But if you have slower networks, of course, you should make even less specific calls instead of doing it the hard way. But depending on how much values you really need to change, it may not matter that much after all. But that's kind of the facts that we know at the moment and what I can say about it. Questions? Yeah.
A small comment about the embedded devices. They are such a moving target.
Yes.
So let's say if you judge from the setup of your PC how it was and how like a modern PC would be now. Like the embedded devices have progressed much faster.
Yeah, that's true.
So that's I wouldn't expect if the first version of the Raspberry Pi gave you this 40 times slower. Now the Raspberry Pi 2 and then some alternatives that are running the same Raspbian, but like they have Chinese processors that are like 10 times faster than the Raspberry Pi 2, then you would get quite good performance.
Yeah, that is true. That's true. And therefore they will be just more and more usable for anything. Mika?
Will you provide the source code of these test cases?
Yeah, we could probably consider that. It's the client application is made also based on our sample console client, which is part of the Java SDK. It's just kind of parameterized to be able to instantiate several client applications and so on. But yeah, that would be a good idea to kind of make it also public so you can use it yourself too. Okay, more questions about this? How are we in time? Just 5 minutes past. I reserved the last place for myself, so I don't need to worry about the time, but I'm still in schedule. Okay, I think we can have a final discussion. Matthias, Stefan,